Thank you all for joining us today to hear the webinar about the introduction to TrueLoad. Okay, my name is Tim Hunter. I'm president and founder of Volstar Technologies and the original developer for TrueLoad. What you see on the screen here is an example that we did with the University of Wisconsin-Milwaukee several years ago with their SAE Baja car team. They wanted to know what the loads were on their suspension arm here, and you can see here how we calculated the loads and showed them what they did. And we're actually not going to do a deep dive on this today, but if you want to learn more about this, this paper is on our website, so please go to our website, download that paper if you want to learn more about it, and we've got other really great papers on our website too. So just getting right into it, here's what our agenda is today. The presentation is going to be about 45 minutes long. Yeah, my rehearsals, it was closer to 40 minutes long, but this will be about 40 to 45 minutes long, and we're going to go over what is TrueLoad, the motivation for TrueLoad, what is load reconstruction, and how are we verifying these reconstructed loads, okay? We'll go through the TrueLoad workflow in a pretty detailed fashion here. And then once you got these accurate verifiable loads, what's next? So we'll explore some possibilities there, okay? So this is kind of what we're going to cover today. And at the end, we're going to have about 15 minutes or so for Q&A, all right? So hopefully we can answer all of your questions here. So a little bit about me. So I founded the company back in 2010, and I founded the company and I developed the first versions of software here for the company. Since then, we've hired some staff here. For example, we've hired on Annie Perillo, who's our senior software developer, and she's taken over most of the coding of the software these days. I still come up with big brain ideas, and I have Annie code them up for me. And then I'm involved with my clients' consulting work, and also we do training and support, and I get involved with the training and support as well. So I'm very much involved in the company here, but we're trying to spread things out a little bit too. Prior to that, I was at Harley-Davidson for 22 years, and it was a fantastic job. I worked in product development, and every aspect. I was a structural analyst my whole time there. At the end, I was chief engineer of vehicle structures. I had a staff of 77 people, and I had CAD engineers and designers. I had structural analysts. I had test engineers. I had manufacturing engineers. I've been involved in every aspect of product development. I think I understand what you all are going through on your day-to-day business, and you'll see here today that we've got a really great tool that can really help you out and help you get your product to your products to market faster. Okay, so sit tight, and we'll take a look at all this stuff. So TrueLoad, what is TrueLoad? TrueLoad is the original load reconstruction software. We were first to market. We brought this technology to market, and frankly, we're not only first to market, we're frankly best to market. We've got the best product out there for doing load reconstruction. So we're going to go through this workflow at a very high level here, and then we're going to dig into it more. But when you're doing load reconstruction here, you want to basically go into your FEA model and basically set up some unit load cases on your FEA model for the loads you want to sense. So we're going to concentrate on this Razor scooter today. So so this operator here, they want to understand the foot loads, XYZ foot loads, and the wheel loads, XYZ wheel and axle loads back here. So they basically go into their FEA model, set up these unit load cases on their FEA model, and then they run the analyses on those unit load cases in their FEA model, and then they bring that into the TrueLoad pretest software, and the pretest software tells you where to place the strain gauges on the part in order to sense these loads that you've modeled in your FEA model. And what TrueLoad software is going to do then is going to construct a correlation matrix that relates strain to load. So basically, we're going to have the strain to load correlation matrix. We're going to store that to the disk. And then with these strain gauge locations located, we're going to go into the physical world now, and we're going to instrument up our components with these strain gauges. So we're going to instrument up strain gauges, and then we just collect strain data. So we can collect strain data in the lab, in your proving grounds, or even in your customer hands. We just need time history of strain. And then once we've collected that strain data, the whole point of the exercise now is to calculate loads. So now we've calculated these loads here, and with the true load post-test software, and now that we've got these loads calculated, our software automatically goes back inside of the FEA model and pulls out simulated strains at these strain gauge locations. And then we plot up simulated strain on the vertical axis and measured strain against the horizontal axis for all the gauges. And what we get are these nice one-to-one correlation lines. So if we're able to match the strains in the real world with our loads, then our loads must be right, and then we can go off and do great things like operating deflection shapes to understand what the full structure is doing. So this is basically what load reconstruction is doing, okay? We're able to go in and leverage our FEA model to work with test data in order to get the loads that are actually happening on the structure, okay? This is what we're all about. So with load reconstruction, the loads are accurate because the process has been optimized, and our results are automatically checked with strain correlation. So this is super important. And it's not just load reconstruction that we're doing. We've got a complete product development environment. So we've got so many great tools in there. We've got a workflow that we've developed over 40 years of product development. We've got many ease of use features in there. And we've got some super advanced features in here, like sliding loads and contact control and design of experiments. So we can do some really powerful things with the loads and the loads we're measuring here. And what's really great when you get involved with us, we give you great training and great support. We are really committed to giving very high level hands-on support to our customers, because we want to make our customers succeed using our software, because when you succeed, we succeed. So we want to make sure that you have successful applications of our product on your applications. And our software frankly works on any product of any size in any domain, So if it could be as small as a can crusher here to a razor scooter to airplane wings and heavy equipment, even army tanks and bipedal robots. These are all customer examples here, just showing how we can apply this technology to just about anything you can think of. If your product is experiencing strain, we can turn that strain into loads. And our marketplace is pretty much what you'd expect: aerospace and defense, automotive and transportation, industrial machinery, heavy equipment, and marine. Basically, these are the applications that have these products are undergoing unusual loading and strains that we can go in and back calculate what's happening to them. And as you can see on the screen here, these are just some of our customers who are leveraging our product to help them doing better product development. So the motivation behind TrueLoad. So what's the motivation behind TrueLoad? It's frankly, what's the load, right? So here, if you're an engineer who's got to design parts for this motorcycle, right? And if you've got to design parts that function and are durable, but the loading on this motorcycle is crazy nonlinear. You can't measure the loads, you can't simulate the loads, but you as the design engineer, you're still responsible for making parts that are functioning and are durable. Well, what do? Well, we recognize that the subsystems on this motorcycle are basically responding linearly. So we're going to put strain gauges on the swing arm, the crankcase, the handlebars, the fuel tank, the luggage system, the fenders. We'll put strain gauges in all these subsystems and let these subsystems become their own load transducers. And then we can use those loads to design and optimize those subsystems, okay? This is what we're doing here, okay? This is a first-to-market solution, like we said earlier. It's based on the science of influence coefficients. Influence coefficients have been around for a long time, but the problem with influence coefficients historically is that people would guess where to place strain gauges, and then they'd set up very elaborate, expensive tests in their labs to put unit loads on the structures. And with guessing at the strain gauge locations, they would get poor correlation matrices. And then when they went to the field to measure the loads with those strain gauges, they would have very, very poor results, and it never quite caught on. And the problem is they just weren't doing it right on the front end. And what we're doing is we're leveraging the FEA model, scripting and optimization to get the optimal correlation matrix and the optimal placement of strain gauges, okay? So if you basically leverage the tools you got and use the right optimization strategies, we can do this right and get good answers the right way. So, companies try to understand the loading using traditional means. The most traditional approach here is using load transducers, like you see on the screen here. And these load transducers are perfectly good, valid devices. They are wonderful things. Okay, they're highly calibrated. They're great devices. There are issues with them though. Okay, they're expensive. So these things can cost tens of thousands of dollars to even hundreds of thousands of dollars to buy. And then every time you use these, you've got to modify your structure to use them. So you basically got to cut out a part of your material, insert the load transducer into your structure, and now you just change the stiffness, you've changed the mass, you've changed the load pass, you're measuring something. It may or may not be the actual loads. And then to add insult to injury, when you bring those loads into the structural analysis team, the analyst is typically working on the as designed part, and they've got to rework their FEA model to look like the test part in order to use the loads you just measured. Okay, so it's not great, but this is a traditional approach that people use. Okay, another approach that people try to use are strain gauges. So typically what will happen is that typically an analyst will look at their FEA model, come up with some strain gauges locations based on the contour plots in their FEA model. They might talk to their buddy and say, come up with some more locations. They might come up with, maybe 30 strain gauge locations. They go instrument up the part, get those strains back from the proving grounds, and they look at the strain responses from the proving grounds, and they just scratch their heads. The strain response in the field is so much more complex than what they're seeing in the FEA model, because the loading in the real world is so much more complex than what's in the FEA model. And so typically what will happen is you'll pick one or two channels of data at one or two points in time, and you'll work for days, if not weeks, just getting those two areas to light up qualitatively the same way. I'm not talking quantitatively, I'm just talking qualitatively the same way, and say, yes, that's my load case. And then you go in and then you start redesigning your part with these new loads. And then the next time you get to your proving grounds with your new parts, you found out you've got the same mistake and you're doing it all over again. And another thing that happens when you're doing this is these time histories can be very long, right? If you come back from the proving grounds, you might have a time history that's 500,000 data points long. And the problem is that for each point in time with these strain responses, each one of those points in times demands its own unique loading recipe. So if you've got 500,000 data points, now you got 500,000 loading recipes, and you just can't do that by yourself. So you're really kind of stuck in this whole situation of GIGO, right? Garbage in, garbage out, and you're doomed to repeat this design, analyze, build, test cycle over and over again. We don't want to do this. This is slow and expensive. We don't want to do this, okay? So this has got to go. So there's a better way. So the solution here is TrueLoad. We're going to do what's called in situ load measurement. In situ means in location load measurement. We're going to turn complex components into multi-channel load cells. We get to leverage the FEA model to work with the test data. We can work with any FEA. We've got really nice plugins, for instance, Workbench, Abacus CAE, SimCenter, and FEMAP. But at the end of the day, you're using our software to get the optimal placement of strain gauges. And now once you've got these optimal placement of strain gauges, you're going to get strain correlated loading. So now you've got the strain correlated loading. You can explore redesign efforts here with that loading and with our tools. Or if you want to go off to your third-party FEA-based fatigue softwares, you can bring these strain correlated loads in to do that. And now you'll actually get meaningful fatigue results from your softwares like FE-Safe and others. Okay. So what is load reconstruction? Well, we're calculating operational loads from strain measurements. So how does that work? Well, we recognize that loads are proportional to displacements. Displacements are proportional to strains. Strains are proportional to loads. This is a linear system, okay? Now, we fully realize everything in life is nonlinear, okay? We understand that. We really, really do understand that everything is nonlinear, okay? But what we're doing is we're turning your parts into load transducers. So we're going to stay away from welds. We're going to stay away from bolted joints. We're going to stay away from areas of contact. We're going to be in nice nominal areas on the part where the strain response remains linear and proportional to the exterior loading. okay? So we need it to stay proportional, linear and proportional. The loading can be as nonlinear as anything. So it could be sinusoidal loading, it could be ramp loading, it could be impact loading. That can be fine. We just need to maintain that linear proportionality to the strains and the exterior loads. So I can take this little triangle here and turn it into a couple of equations, okay? So the first equation here is F equals Kx. Well, that's Hooke's law, right? The fundamental equation of mechanical engineering. That's the right-hand side of this triangle, right? F equals Kx. So if your structure is obeying Hooke's law on bulk, you can have local plasticities, but if it's obeying Hooke's law on bulk, then the left-hand side of the triangle's got to work, which is strain times correlation matrix is equal to loads, okay? And we're going to calculate loads by taking strains from test times a correlation matrix from FEA to equal forces from strains, okay? This is how we're calculating the loads. This is how we're doing it. And once you got those loads, you can do great things like operating deflection shapes. So this is what's going on here, okay? So, and now that we've got this capability with TrueLoad, it's going to make us be able to do virtual redesign and FEA-based fatigue possible, okay? And we'll be able to be doing virtual tests and FEA designs instead of physical tests. We get to do virtual redesign. This is what we're always trying to do in engineering. We always want to do virtual redesign and not going back to physical tests. And our operational loads can now be passed into our fatigue packets, so we can do the FEA-based fatigue. This is another thing that we always want to do in engineering, is do FEA-based fatigue. So we're making this all possible because when the loads are accurate, the results are accurate, okay? It's that simple. So how are the reconstructed loads verified? Well, I kind of hinted at this earlier in one of my earlier slides. It's the slash, right? The slash makes it all possible. So in TrueLoad, in post-test, we're going to go in and use our calculated loads from TrueLoad and go in and pull out simulated strains at the strain gauges, and we're going to plot them on the vertical axis of our cross plot here. And on the horizontal axis, we're going to plot our measured strains for all of the gauges, and we're going to get these nice one-to-one correlation lines, which shows that if we're matching the strains in the real world, then our loads on the FEA model must be right. All right, so this is fantastic. And and the calculated loads are accurate in the real world from the real world loading. If the strains are right, the loads must be right. So just wanted to throw this slide in here. This is from a recent consulting job we did for a customer on their proving grounds. They had a vehicle running over their proving grounds, and we had a bunch of strain gauges on there, probably, I don't know, 12, 15 strain gauges on there. And we're getting one-to-one correlation on those things, okay? And these were pretty rough durability cycles that we're going through here. And this is what you get. And with TrueLoad, I mean, this plot was literally generated with one button push, okay? Get the model set up, push the button, walk away, and you get these plots, half an hour later. So it's fantastic. So we're going to go through the workflow for TrueLoad, okay? How to get accurate verifiable loads in 4 steps, okay? 4 steps, that's all it takes, guys, is 4 steps. So step 1 here is we're going to apply unit loads to our FEA model. So these are just your FEA models, okay? You set up your FEA model any way you want to. But rather than putting in a complex load on your model, I'm going to have you decompose it to a series of unit loads. So like on this Razor scooter, I put in 1 kilonewton XYZ at the foot, and 1 kilonewton X on the axle, and 1 kilonewton Y and Z at the tire patch, okay? So I've got these 6 unit load cases on my FEA model. So this is it. So you just got to go in, think about where does load come in, and put unit loads there, okay? So these just need to be unit load cases. That's all they are, all right? And then we go into the pretest software, and the pretest software is going to look at all those strain results for those unit loads, and it's going to query the model and find out the optimal strain gauge placement here. And you can see here, it's gone off and it kind of picked this pattern of gauges on the bottom of the Razor scooter here. And you can see there's some gauges are horizontal and some are vertical. So it's figured out how to orient these gauges to best sensor loads. And then we had some gauges up here on the top too. So basically you have these gauges then indicated by TrueLoad pretest. And now once we've got that strain gauge placement, then it basically from the FEA model, it extracts a correlation matrix that relates strain response to load, and we store that correlation matrix to disk, and we take this gauge placement information now, and now we bring that into the testing world. So then we instrument up our razor scooter with all of our strain gauges here. So we instrument up the razor scooter on the strain gauges. And then once you've got those strain gauges hooked up, we wire them up into our data acquisition system. We use a DTS slice micro. You can use any data acquisition you want, but this is the data acquisition system that we use. And now that you've got the data acquisition system, you just exercise your part however you want to exercise it, and you collect time histories of strain data. Okay. So now we've got the strain data, and now the last step here is what we're coming here for, is we want to get load. So we take that strain data, we run it through the post-test software, and it's going to generate these time histories of loads now for our 6U load cases that we put on back on in the first step. And from that, it goes into the FEA model, pulls out simulated strains on the gauges, and plots them against the measured strains. And so we get the cross plot of simulated strain versus measured strain. And then once we've got that, then we can then drive that into our software to generate things like operating deflection shapes. And you can see these nice little load vectors here of what's going on. Okay. So it's really that simple. Okay. That's how we're doing it. So now we've got these loads. Well, what's next? Okay. What you can do with these loads now that you got them? Okay. So we can do virtual design iterations and FEA-based fatigue. So let's go through this here. So this on the right here, you're kind of seeing a header from our post-test report, and really when we get into it, we've got these time histories of loads, as you can see here on the screen, and what gets generated is what we call a quasi-static event file, or a QSE file, and this file here is going to point to the FEA database that you brought in, and it's also going to point to this true function file, which is basically a file that is storing the loads that we just calculated. So this quasi-static event file points to a FEA database, and it points to this loading file with these loads that you see on the screen here. And then we can do anything we want with it. So we can go in and we can explore the part using our true quasi-static event software, true QSE software. We can generate operating deflection shapes. We can export it to durability software. And we can export the loading function. So if you want to take these functions and push them out to something else or bring them into your FEA tool, you can still do that. And what we're all coming here for is to do redesign. We really want to do redesign, so we can do that as well too. So let's take a look at these steps in detail. So here, we're going to explore this in true QSE. So on the right of the screen here, I've got a recording of me using our true QSE software to explore things, and I'm just going to kind of talk over the video as it goes here, and we'll see how it goes here. So I'm just going to get this video going, and what I'm doing right now is I'm launching the true QSE software, and I'm going to load up the quasi-static event file for this razor scooter that we've got, and it's loading in right now. And then I'm going to make this screen smaller so that we can see things nicer on the screen here. Bring it down below so we can see what's going on. And we're going to plot up the load functions that we just saw. So we're just going to plot those up real quick. So there's our loading functions. And now we're going to take an isometric view, and we're going to go and say, let's take a look at a few nodes and see what's going on here. So I'm going to pick some nodes here. So I picked one node, and then what I'm actually doing is I'm trying to think of where I'm going to pick next, but I'm going to pick like kind of nodes on each side, 2 in the back, 2 in the middle, and 2 up front. So just pick a few nodes here. All right. And then let's take a look at displacements. So we're going to basically say, hey, let's take a look at X, Y, and Z displacements, and just say apply. And then what you see here now is we get a plot of the displacements, and let's turn off the and then we can say, hey, there's a big displacement. Where's that happening? Oh, that's where the big displacement's happening. That's interesting. And let's take a look at some smaller displacements too while we're at it. Let's go. And there's the smaller displacements there. You can kind of see where those were at. Okay, so that's interesting. You can kind of do that. And now let's take a look at another area where we might have some structural concerns. So let's take a look back at the axle in the rear here. And let's take a look at elements right around that axle connection. So here I'm going to go look at the elemental functions here, and we're going to pick the elements right around that axle. So I'm going to pick a few elements here. We're going to start picking. We're going to pick all the elements all the way around here. So just give it a second here. We'll get them all. All right, so we got all those elements picked. And then let's look at maximum principal strain. So let's go grab maximum principal strain and let's take a look at what that looks like. And let's turn off the legend so we can see what we got. And look, we got a couple of big spikes there. So let's see where that big spike of maximum principal strain is. It's happening right there. What element is that? Let's uncover the element so we can see them. And now we can see where we've got an issue with maximum principal strain. So now if we wanted to do redesign, we've got somewhere to focus on here, okay? So this is kind of just a really kind of brief overview of how our quasi-static event tool works and how once we've got the loads, we can query anything on the model very, very quickly and easily. All right, next thing that we're going to take a look here are operating deflection shapes, okay? So again, in our quasi-static event software, we've got this tool to generate operating deflection shapes, and basically we can take a subset of the time domain. So you see the full time domain of the loads here. We're kind of focusing in on this big spike of the loading here, and that's blown up down below. And then once we do that, we can generate this operating deflection shapes of what's going on. And you can see the little load vectors like we've been seeing here, and that the loads, the corresponding loads there, okay? So this works really easy, and you can generate this quickly and easily. And frankly, this is much faster than you trying to redo these solves in your FEA modeler, okay? These happen very, very quickly versus an FEA solver. All right, and then export for durability. So in our True QSC tool, we've got a whole section of areas where we interface to durability tools. So we've got an interface to FE-Safe, we've got an interface to Hyperlife, an interface to Safe Design by ProLambda, and an interface to Lifing by Airworks. So some of the big packages out there for doing durability. And so basically we can just click on one of those. I'm choosing FE-Safe here, and we're just exporting that data then. And what happens when we click this OK button here to generate the deck, it's going to write us out basically a macro for FE-Safe. We go into FE-Safe, run the macro, and the only work we've got to do in FE-Safe then is basically assign the durability materials to the model. Okay, so it takes about 10 minutes to set up that job, and then you have it run, and then it goes off and calculates the durability results. And so here's my set of durability results for this Razor Scooter event that we've been looking at. And you can see here, there's one little element here that's got the minimum life right up here, up on these welds here on the steering head, and then back here by the axle, we've got some low life here. So now you can see how quickly and easily now we can go in and understand the durability on this thing with just a few button clicks. Okay, so it's really one or two button clicks in True QSC, running a macro in FE-Safe, assigning materials, and go. Okay, it's that easy. And then many people want to export the loading functions. So again, we can go in the QSC software and basically click on the functions tool, and it brings us up into our utility here, which we can look at all the loading functions in detail, and we can export them to CSV files. And so here's Excel here with our loading functions. And again, these are long. So right, basically, if our time history is 500,000 data points long, this is 500,000 data points. Okay, so these are going to be big files, but these are all the loads for your event, and you can do with them what you want. If you want to bring them into your FEA modeling tool, you can. If you wanted to bring them into other external tools, you could do that as well too. Right. And then finally, we've got redesign here. All right. So everything we've done so far has been looking at our design, right? Our baseline design that we measured loads on, right? This has all been a rear view mirror look, right? So we've been able to take a look at everything that was going on with our part, explore the durability, look at the responses, look at operating deflection shapes. We can really fully explore our part from tests fully, okay, in ways that you've probably never been able to do it before. but we're in product development, okay? The whole thing that we want to do in product development is we want to do redesign, okay? So we're going to show you how you can do redesign with our tools here, okay? What I've got here is another video from a webinar we did several years ago using this, and this is just part of this webinar showing a redesign on this Razor scooter. And so I'm going to play that video. It's got a voiceover here, and pardon me, guys. I'm just thinking of something here. I just set up my presentation wrong for 1 second, so I gotta back out for just 1 second here, and then we can come back in, and then we'll play this video. So I'm sorry about that. I'm going to say share again, and I'm going to say and include sound. I forgot to include the audio when I share the screen. I'm sorry about that, guys. So here we go. So this is going to be going through playing this, recording this webinar we did several years ago. This webinar has got some links on it. There's some links up here at the top and some QR codes. These don't work, okay? So don't try to go to these links or QR codes. These are not going to work here, okay? So just ignore those. But here, let's just sit back. It'll be about 3 or 4 minutes of this video, and we'll move on from there. So here we go. So here's an operating deflection shape of our Razor scooter. And this graphic here, I put a section plot through it so you could see the load vector at the foot there, just so, so you could, because it's kind of going inside of the structure, so you can kind of see the load vector there. And so here we're just seeing a subset of the time history here for our animation. And so this is great, This is great. We get to see what our Razor scooter was doing, right? We've got very highly accurate strain results on our Razor scooter, and we're able to see what's happening on the Razor scooter. So this is fantastic. But we want to do redesign, right? The whole point of this is that we're in product development. We need to iterate and do redesign. So let's do redesign, okay? So I went into the FEA modeling tool, and I made some redesign here. So I came up with this little pattern of these little triangular shaped holes in here. So I pushed this through the structure here, and basically took out all these little holes in my little footboard for my Razor scooter here. It was a 9% reduction in mass. It might look cool. I don't know what cool is, but there you go. And then we can just then all we need to do in the FEA model is rerun those unit loads on our redesign model, and we can come back into our true QSE software, and we can regenerate the operating deflection shape based off those same loads now. These are the same loads that we saw before, and now we see the stress and strain response for our redesign, okay? I mean, the longest part of this whole thing was me figuring out how to push holes through my FEA model, okay? I was doing the CAD work on this. Once I had that, solve the structure really quickly in FEA and bring it back into true QSE, and away you go. So the hardest part for me was doing the CAD work, okay? And then once we went into all this, we can look at the responses here side by side, and I've got a cutesy little thing here. I'm just going to bring another window up here. Let's see if I can get this going. So we got the two structures running side by side. So there's our baseline design, and here's our modification. And yes, we get stress risers here. We get some increased stress here because of my cutesy little pattern. But nominally, that's not a big deal. It's nothing that we'd be too concerned about. Okay, everything basically performing more or less the same. The only concern I would have here on my cutesy design is these points in my triangles here. I've got stress risers going on there, right? So if I were to do it, if I were to finalize this design, I'd probably want to go and put some fillets in on those triangles and to take out those stress risers there. But that's totally doable, okay? I didn't want to futz around with the CAD anymore, okay? But you get the idea. It's very easy to go in and explore anything that you want on the design now that you've got the loads, and you've actually got the actual loads driving this thing. So you're not making guesses. You know how this is supposed to go. So there you go. So there you go, guys. So there, I'm showing you how we can do a very quick and easy full analysis on your redesigned part using the actual loads, okay? And the interesting thing about that is that the FEA work on this is almost minimal. We're just solving unit loads on the FEA model, and then our tool TrueQSE is back at expanding the results so you can see everything everywhere. So the solution time becomes, in FEA, becomes very minimal, and you get to leverage our tools to get all the answers you need. So it's really a great application here. So here's an we're going to do one more run through on the workflow, just one more summary slide on how the workflow works. So basically, again, we're starting off with the FEA with an FEA model, your FEA model, but rather than putting in complex loads on here, you're going to put in a series of unit load cases, however you want. So, 1 kilonewton XYZ, maybe a pressure load, maybe a thermal load, maybe an inertial load. However you think the load is coming into your structure, you're going to model that in FEA. And then once you've done that now, you're going to bring that model then into pretest, and pretest is going to look at all those strain results, come up with the optimal strain gauge placements, and then we'll give you tools that allow you to reposition and reorient the gauges. And at the end of the day, once you're happy with your gauge placement, we're going to store a correlation matrix that relates strain response to load, and we're going to store that correlation matrix to disk, and then we go into the physical test world. We instrument our parts with physical strain gauges, and then we just measure time histories of strain. So that could be in the lab, in the field, or in the proving grounds. It just doesn't matter. Anywhere you want to measure strains, we can measure strains. And then once you've got those strains now, we bring them into post-test, and post-test is going to take the measured strains in terms of correlation matrix and pretest to generate for us time histories of loading functions. And now these are strain correlated loads, and then you can bring these into your FEA model if you wanted to, but I highly recommend you leverage our TrueQSE software so we can explore the design and evaluate and analyze and iterate on our design in this very nice tool that back expands our results very efficiently. And then by all means, if you folks are using FEA-based durability, well, your FEA-based durability tools will have an engine that brings in your FEA model. They'll have a database of fatigue materials, and they'll have their durability results calculation engines, right? So this is what you're buying from your durability software company. You've got to provide them with a duty cycle. And now you've got strain correlated loads. So this is the best duty cycle you could provide. So now you're actually going to get meaningful results out of this, okay? So this is what we're doing here, okay? And yes, this flowchart looks a little complex. I get it, okay? But really, the first 4 blocks are you turning your part into a load transducer. The bottom flowchart is you doing design and optimization once you've got your loads. So our customers typically do the first 4 blocks once, and then do the design and optimization loop maybe 10, 20, 30 times as they're working on their parts. Okay, this is very typical for how our customers use the software. All right, so we're getting towards the end of the seminar here, the webinar here. Future topics here that we want to bring to you. We want to talk about linear dynamic events. We've got a tool called TrueLDE for linear dynamic events. It's a great tool. We'd like to just show you what we can do and how you can leverage your existing linear dynamic analyses and get a little bit more out of them using our tools. And then we'd love to talk to you about this new technology we've developed called equivalent static modes. It's going to totally change the way that you approach dynamic problems, because we can help you iterate on those dynamic problems super efficiently with our tools and this science called equivalent static modes. It's a really powerful tool that we can introduce you. And then we'd love to show you some great features of our software, like working with known loads, or what we call them hybrid loads, or doing contact or moving loads. So loads that move on your structures, okay? We've got great tools for handling all those things. And we even got really nice tools for using a 3D STL printout to place your gauges on your structure so you don't have to measure anymore. We can basically make you a clip-on template that you put on your parts, and you know where your strain gauges go with no measuring, okay? So we've got some great tools here and many, many more, but we'd love to do some future topics with you all. So stay tuned, and we'll be pushing some more webinars out in the future. And then finally, just to summarize on TrueLoad, TrueLoad is going to revolutionize the way you do product development. We're going to get you optimal strain gauge placement based on your FEA model. We're going to give you strain correlated loads and strain correlated load histories. You get to reduce your test and analysis time because we've got the straightforward approach for doing it, and you reduce your test costs. We're not buying load transducers. We're not modifying structures. You don't have all that labor and testing going on. We're just laying uniaxial strain gauges. It's pretty darn simple, okay? And now that you've got the knowledge of the true loading of the structure, you can make the right decisions. We go through iterations in product development, not because engineers don't know what they're doing. It's usually because engineers don't have the actual loads in their structures. And if I can give you the actual loads in your structures, you're going to make the right product decisions, and you're going to go through your product development time, your iteration time, less and less. We're going to save you tons of money by eliminating your iteration cycles. Many of our customers cut their iteration cycles in half, and sometimes they only do one iteration. It's amazing how we can give you knowledge that can actually get you the designs you need at the right time. Okay, and like I said, we've got all these other great tools here: sliding loads, hybrid loading, content control, and embedded solutions. We'd love to talk to you more about those things, so please reach out to us. We'd be happy to talk to you one-on-one and get into it more. Okay, so I think we're at the end here. So thank you so much for taking the time to be with me today. We've got a short survey at the end. I believe when you get done with the webinar today, you're going to be taken here. But if you wanted to scan the QR code there to go to the short survey, we'd love to hear back from you. Also on here, on the bottom right here is a QR code. That QR code just gets you to our website, and you get my contact details are on here. So let's take out the Q&A and see what we've got here. All right. Just pulling up Q&A here. So, hey, I see a question here. One person's asking, do you need to use rosette gauges? Okay, this is one of the questions I frequently get on my software. Is that people often use rosette gauges. The TrueLoad software, by design, works on uniaxial strain gauges. So we're just using uniaxial strain gauges. So the software is going to tell you where to place uniaxial strain gauges on the structure. If you need to use rosettes, or you've got existing data that uses rosettes, we can give you rosette placement with our software. We can design rosettes in, but the software out of the box works on uniaxial gauges. Let's see, I got another question here. Is there a maximum number of loads or gauges? So the software has no built-in limits to it. So basically, we can handle any number of strain gauges, any number of loads, any size FEA model. The bigger things get, the slower things go. You know that. But really, I mean, we've done problems with 40, 50 loads and hundreds of strain gauges, and that's just fine. It all works fine with that. Let's see. Looking for another one here. Another question here is how do you handle dynamic and harmonic loading? Okay. So a lot of people are working with structures that have harmonics present in them, and so what we do is we have our customers, rather than putting on static unit loads on their structures, we have them basically solve their models for eigenmodes, and basically then they can choose the modes that they're interested in, and we'll lay strain gauges to sense those modes. And then what TrueLoad will be doing, we'll directly be calculating the modal participation factors for those modes. So we basically get great strain correlation, and we get people that directly calculated modal participation functions for their structures. Okay, and so that's a fantastic thing, and this works great for people, but now with our new, we've got this new technology called equivalent static modes, and we've got a technique now that we can give you tools that you can very quickly and easily do redesign with your existing modal participation functions, rather than having to go back through and do eigenmode calculations again and doing more testing again. We can give you some things that we can reuse the work you've already done. And that'd be a great topic I'd love to talk to you about more in depth. So I think that gets to the end of our questions here today. Thank you all. We will be sending out a recording of this webinar, so we'll be sharing this with you all today. So please reach out to us if you've got any questions or you'd like to have some follow up and figure out how we can help you out with your product development environment. Okay, so thank you very much, and that ends our webinars. See you later.